Uniformity. Socrates noticed something about the last level. What was it? I don't know. You tell me. Okay. Do you guys remember we computed? Let me slide this over. We don't need to see this whole thing. Do you remember we computed the there was something funny about our last time. So last time we computed, we showed that the function f of x is equal to whatever, x squared minus 1 is continuous, meaning it's continuous on all real numbers. And when we did this, how did we do it? What delta did we choose given an epsilon? Anybody remember? It says right there. You're getting senile, old man. We chose delta equals epsilon over 2x plus 1. That's what we needed in order to, that's the delta that we needed, right? This function, x squared minus 1, it looks like this. But if you're way far out over here at negative a million or whatever, then, it looks like that. And over here, I'm trying to not to get in the way of the text. I mean, yes, it's continuous, but it's rising very, very rapidly, right? Its derivative is like x. And so if you want a small change in the height, you need to have a very, very small change in the x. It depends on what x is. Okay. So is there anything interesting about that? Well, it has an x in it, but we have no other choice but to put an x in it. We looked at this difference, f of y minus f of x. We found that it was y minus x times y plus x. Y minus x is of size delta. Y plus x is, y is x. Y is near x. So that's 2x, and then we added 1 just to be safe. We had no other choice but to have a factor like this. It's actually not true otherwise. Socrates says, okay, just put a pin in that for a minute. We're going to come back to that question. Let's go to another question. Suppose we have a sequence of functions, fn, and a sequence of functions, and each of them is continuous, and they converge to some limiting function f of f. What do I mean by that? So fn converges to f pointwise means what? Joe?
What's X R?
Yep.
Sequence of
Exactly.
capital F.
Exactly. Exactly right. This sequence of functions, this sequence of functions converges to f of x. Okay. So for every single point, the fact that you have a sequence of functions means now you have a sequence of points when you evaluate those functions at x. And there's also a limiting value, f of x. And does this sequence of points converge to this point for every x? Okay, that's pointwise convergence. Fine. What can you tell me about f? So if all the fn's are continuous, then and Simplicia says, is S continuous? Wait a second. I've fallen into this trap before. We talked about this on day one. On day one, we noticed that the functions, even on 0, 1, forget about the whole real line. On 0, 1, if you look at the power functions, fn of x is x to the n. Okay, so here's 1, here's 0. 0 to the n is always 0. 1 to the n is always 1. And then you have your straight line, and you have your parabola, and you have your cubic, and you have your quartic, and so on. So for every point on 0, 1, fn of x converges the sequence. So you fix x in 0, 1. This sequence, as n goes to infinity, converges to, Joe?
0.
It depends. Exactly right. 0 if okay, you take any number less than 0 and you raise it to a very high power. in the limit, you're going to get 0, unless that number was already 1, in which case you get 1. Okay? Then nothing. There's nothing I can say about the limiting function. And what do you think is the problem?
My problem being like, why can't we say?
Why can't we say that the limit is continuous? What breaks down? So,
Algebraic theorem. If it's like infinite.
yeah, I think of the algebraic limit theorem as I have a limit, and then I do some algebraic operation. Multiply things, I multiply by a constant, I take reciprocals. I'm not doing any of those. I just have arbitrary continuous functions. They're converging pointwise to some function. How come that? Obviously, that function can't be continuous, but where does the argument go wrong? So what would be a hypothetical argument? Well, very good. Yeah. In the past, whenever I've said what goes wrong, the right thing to do is argue by contradiction. In this case, there is something that goes wrong. So we're not going to find a contradiction. I'm trying to understand, where does the argument break down? What are we missing? How come we can have a sequence of continuous functions converge? They're converging pointwise, and what they're converging to isn't continuous. Well, let's try to prove that. Let's do exactly what you said. Let's just follow the argument as far as we can until we reach a point where we're trying to prove something that's not true. Okay? So each of the fn's is continuous, but the limiting function is discontinuous. Okay. So mere pointwise convergence is not enough to guarantee the continuity of the limit. Let's pretend that it would be and see what goes wrong with our proof. All right. So we'll try to prove. So theorem, pointwise limit of continuous functions is continuous. Okay, it's theorem in quotes because it's not true. Just true. Let's record this in case you're reading the lecture notes later and you see this theorem and you decide to quote it. Okay, so no, it's not true. Proof, fake proof. All right, so we want to know that capital, is capital F continuous at X. So fix yourself in X. Let X be given. Okay, I'm just going to draw some hypothetical. Here's my limiting function, capital F. I have a bunch of functions, little f, that are converging to it. These are the fn's. And here's some point X. Okay. So if f is continuous, then it's continuous at every point. So fix a point and let's investigate continuity at that point. What does continuity mean? For all epsilon, yeah, we need that for all epsilon, there exists a delta. So that for all y, continuity, we don't have to say not equal to x. Just for all y minus x less than delta, f of y minus f of x is less than epsilon. Okay, so give me a neighbor. So I have some value f of x, whatever it is. Give me a neighborhood, give me a window. So this will be f of x plus epsilon down to f of x minus epsilon. How far out, what delta? I'm trying to find a hypothetical delta. What value of delta would guarantee this bound on f? Okay, let's say we had such a delta. I don't know where it's going to come from. Say we had such a delta. Say we had such a delta. The inequality, the key question is that these are supposed to be capital F's, our limiting function, capital F. The key question is about capital F of y minus capital F of x being less than epsilon. How could we get these things close to epsilon? Well, what do we have to reach to? This should smell like our proof of completeness of the real numbers. We had Cauchy sequences converging to points, and points being themselves Cauchy, and we needed to take some kind of diagonal type argument. So the Fn, the Fx's are limits of Fn's. So taking little n greater than some capital N large enough, we can make Fx different from little f n or capital N or whatever, less than epsilon over 3. How about f of y? Taking n, again, large enough, we can make f of y minus f, well, let's call this m. And maybe this is also m. Fm of y less than epsilon over 3. Okay? And then maybe we can make it so large. I mean, just make it so large that this is the same n. Oops. So this is the same m. We have some lower bound, right? The fn's are converging pointwise to y, to capital F at y, and the fn's are also converging pointwise to capital F at x. We can make each of these less than epsilon over 3. What do we know about the fn's? They're continuous. They're continuous. Yeah. So the fn's are continuous. But fn's are continuous. So if, as long as y minus x is less than delta, fn of y minus fn of x is less than epsilon over 3. We add these 3 epsilon over 3s, and we're done. But it's not true.
What delta would we choose since n is, that's just one delta for one value of n.
Exactly. There's another place where things, yeah. So this is one, that's true. There's another place where something goes wrong. I mean, if I really could fix an Fn, this wouldn't be a big problem. I say, take n large enough so that this inequality is okay. And then for that n, I get a delta. Fine. So I get a delta. That tells me how close to make the original y to x. There's something else. There is a problem, obviously. The proof can't work. The question is, where is the problem?
Because you're saying like take n, but like you're assuming it's the same, but actually two different n's.
That's right. So I'll take the worst of the two.
But does it always work like that? That you could just take the worst of the two and still close? Like I know in the past we could take the max or add them to something.
I can take the worst of the two, but it's not 2. It's not 3. Why? Where's the instant where we secretly used an infinite number of n's without realizing it? Anybody see it? Right there. Why? Because there's infinitely many values of y. X is fixed. For any particular value of y, I'll get an m. But I need this to be true for all values of y near x, arbitrarily near x. Each one of those comes with its own m. M is a function of y. And if I want to be able to do this uniformly, well, I said the key word, I don't have uniformity. The delta that I get depends on x, and the delta that I get here depends on y. And that's not good because I get different deltas for different y's. So this is really, delta sub y. And who's to say that the minimum over all possible y's isn't zero? In fact, it can be zero. That's what happens with the function x to the n. The delta that you need for any one function, for any one of these functions, it is continuous at 1. But as you go farther and farther out, the delta that you need gets worse and worse. No matter how close you are to 1, if you want to get within, epsilon over whatever, your favorite epsilon, the set of deltas shrinks as n's go to infinity. And in the end, you don't have any delta to hang on to at all. The limit is discontinuous. Okay, so the problem's right here. This m is not uniform. It depends on y, and I need it to be true for every single y in a neighborhood of x. Okay, does that make sense? So this is the part that we can't do. And this is where we need something to, we want to be able to say that limits of continuous functions are continuous. It's just not true, so we need to change the definition of continuity slightly, strengthen our notion of continuity so that we get a theorem that's true. So let's try. So Simplicio says, let's try. You give me an epsilon. I need to find a delta so that for all y within delta of x, I get this difference, right? So Fn converges to F pointwise. For our given x and epsilon, there's some big enough n so that as long as little n is greater than capital N, Fn of x minus f of x is less than epsilon over 3. No problem. And now this Fn is continuous at x. So we can find some delta, depending on n, so that for all y within delta of x, Fn of y minus Fn of x is less than epsilon over 3. No problem. Okay, go on. So then I want to show that this, we use the triangle inequality. These two things, the second thing and the third thing are indeed small. How about that first thing? F at y minus Fn at y. What can you say about each of the three terms? Well, the middle term is less than epsilon over 3. The last term is less than epsilon over 3. I just need to make the first term less than epsilon over 3. Can you? Since Fn converges to f at y, there's some m which depends on y, so that as long as n is greater than y, this holds. But what's the problem? The problem is that n was chosen specific to x, but it needs to work at, this is another way of saying it. The problem is really that this m depends on y. And as you get y, as you range over y closer and closer to x, you might need larger and larger m's, in which case there is no delta that works for all y in a range. And that's exactly what's happening to this function x to the n. Okay, it's shearing. The deltas are just getting smaller and smaller and smaller. For any particular value of Fn, you do have continuity, but just like the continuity of 2x x squared minus 1, why did we talk about x squared minus 1? Because that continuity, the delta, depended on x. And we said, who cares? We care. If the delta depends on x, then you might not have continuity. And you really, not just you might not be able to prove it, it might be false. Okay, so what we need is a better version of convergence where the delta doesn't depend on the value of x. Okay, so what's the matter? No matter which y you pick, you can always find some m. Yeah, so what's wrong? But for one y, you might need m equals 100. For another, you might need m equals 1,000. For another, even closer, you might need m equals 1,000,000, 10,000, whatever. So the original n was fixed, but it needs to work for all y near m, and I need infinitely many m's, and so nothing can happen. Okay, so even though Fn converges to f of y, it is true that Fn converges to f of y for every individual y, but there might not be a single n that makes that convergence happen fast enough simultaneously for all y's in the neighborhood. All right, so the notion that we need is a uniformity. So this is the notion of, we've discovered the notion of uniform convergence. What should we mean by that? So you tell me. What should it mean? So definition. So we have fn's converging to f uniformly. Maybe we'll make this capital F just to make life a little bit easier. If
You mean all Y and then somewhere?
yes, let's write down the definition of pointwise convergence. Fn converges to f pointwise. Pointwise is exactly what we've just been talking about. Okay, so what was it? You give me an x, so for all x, and for all epsilon positive, which we could have done the other way. For all epsilon positive and for all x, same thing. There exists a delta such that yada yada. For all y, yada yada. But that delta can depend on x. You give me the x first, then I give you a delta, like epsilon over 2x plus 1 or something. The uniform version does what? Safin.
Use the order.
Exactly right. You swap these two. For all epsilon, there exists a delta that will work for all x's. So that for all x, and then for all y, within delta of x, fn, let's see, how do I want to say this? It's not about continuity, it's about the sequence converging. The sequence converging. Let's fill this in actually. So this says at the point x, the sequence. So it's not that there exists a delta. It's not about delta. It's about n. There exists an n, right? The sequence of fn of x's converges to capital F of x. So there exists an n, so that for all n greater than n, what? Fn of x minus big F of x is less than epsilon, right? That's pointwise convergence. You give me the x, and then fn of x's converge to f of x as a sequence, which means for all epsilon, there exists an n, so that for all n, yada yada. And what we have to do is swap the order of n's and x's. So for all epsilon, there exists an n, one n, and for all n, so that for all x and for all n greater than n, the same thing. Fn of x minus big F of x is less than epsilon. Okay, does that make sense? So we want to swap that this capital N should not depend on what x is. It should be the same whether you're at x or at y. That same value should work, and then the proof will go through. So the key difference, right? So uniform convergence means for every epsilon, there's an n, so that for all little n greater than capital N, Fn of x minus f of x is less than epsilon. And you can talk about uniform convergence on a subset, uniformly convergent on 0, 1 or something. We'll just talk about the entire real line for simplicity. This thing right here, where you flip that for all x and there exists n, as opposed to there exists n for all x, is exactly what Cauchy got wrong the first time he did this in 1811. He claimed that uniform limits of continuous functions were continuous. And what he actually meant to say, his proof was right, but his proof assumed uniform continuity implicitly. He forgot that the n might depend on x, and his proof assumed that it didn't. Anyway, he didn't do things exactly, and this is a modern kind of reformulation of what he was saying. This was the battle between, we have now solved, there are several things I promised you on lectures 1 and 2, and I only have a couple days left to pay the tab on all of these. So now we're paying the tab on one of the major ones. When are limits of continuous functions continuous? Continuity itself is not enough. You need uniform convergence. And if you have uniform convergence, so this is what Cauchy got wrong in his first attempt at proving that limits of continuous functions are continuous. If you assume uniform convergence, then it's true. Okay, does that make sense? Any questions? Why we need this concept, why this subtle thing about changing the order of the quantifiers makes all of the difference between a true theorem and a false theorem? Something.
So basically, the fact that we're putting the n first means that, well, I know we don't have a delta here, but the delta now can't, if we were to have a delta, it cannot possibly depend on x because the x is chosen after choosing delta.
Right. It's the same. So once we choose an n, then we have an f. And once we have an f with a fixed value of n, like we'll take little n equal to capital N, then we have a delta. And then this epsilon over 3 argument works just fine. We need 1 at f of x. That we get just from this convergence, from pointwise convergence. But we need 1 at f of y, and we don't know what y is. And this says, I don't care what y is. This will work for any x or y with the same n. Whereas this one, you give me the x first, only then can I give you the n. But I have to give you a continuum of y's nearby. Each of them might have a different n. And as y gets closer and closer to 0, those n's might be going off to infinity. And then you never actually get the inequality that you want.
So the above statement implies the below one?
Absolutely. Uniform convergence implies pointwise convergence. In fact, that's a good little easy homework problem. Well, I wanted to talk about homework too. We can talk about that later. Uniform convergence implies pointwise. Yeah, that's a good homework problem. Yes. If you can do this uniformly, then you can certainly do it pointwise. The converse is just not true and is necessary for the limiting function to be continuous. Okay, any questions? Let's go. I wanted to warm up. Before we do this, I wanted to do something easier. Let's go back to typewriter mode, please. So before we prove that theorem, let's warm up with an easy theorem. This theorem is not that hard. The hard thing about this is figuring out what you want to say and making what you want to say not false. Once you've done those two things, then the theorem really works. But first, some things about continuity are not complicated. I wanted to do this last time and we ran out of time. About continuity are not complicated. For example, composition. So this is a theorem. The theorem is called, did I give it a name? Comp. So continuity, if you compose continuous functions, it says f is continuous and g is continuous, then our goal, if you couldn't guess from the name, is the continuity of f compose g. Okay, so so here's a graph of f, and here's a graph of g, and here's a graph, all my graphs look the same, f compose g, whatever it is. Okay, so we're at f compose g. We want to know the continuity of this. So you give me an x. How am I going to find, and you give me an epsilon, and you give me an epsilon. So this is whatever this is. I'll just call it L. So this is L plus epsilon, L minus epsilon. You give me a window epsilon. How am I supposed to find a delta? Joe?
You're gonna find delta you need for f,
Yes.
and then you need to find the delta you need for g.
Yes.
It's within that delta. We need more things.
We just need to draw some more pictures. You're absolutely right. This is f of g of x. So so f is continuous. We're evaluating f at g of x, not at x, but at g of x. So at g of x, f is continuous. You give me an epsilon window around g of x, I'll give you an epsilon 1. Maybe that's what you mean by we need some more. So this will be a window like g of x minus epsilon 1 up to g of x plus epsilon 1. Right? We can force f to be within epsilon by making sure that g is within epsilon 1 of g, of itself. And if g needs to be within epsilon, so then here's x, and here's g of x. And if I need g to be within epsilon 1, this is g of x plus epsilon 1. How do I enforce that?
Since g is continuous.
Yes.
You just specialize using epsilon.
Exactly. Okay. So this is really easy. So let's write out the proof. So proof, we want to show the continuity of F compose G. So give me the X. So intro X. Give me, so now we want to show that F compose G is continuous at X. So give me the epsilon and give me the fact that epsilon is positive. We're going to stick this epsilon and the fact that it's positive into F. So this is called HF, I guess. HF is that F is continuous. HG is that G is continuous. So then specialize, or maybe not even specialize, we can jump a few steps. If I start with HF, what is the first thing that HF wants to eat? A point. It's continuous at all points. It wants a value of X. What is the value of X that I should feed into it? G of X. I want to feed in G of X. So I feed in G of X. Then it wants to eat an epsilon. So epsilon and the fact that epsilon is positive, that says there exists a delta. So choose, but we're not going to call it delta. We'll call it epsilon 1. H epsilon 1 using this. Okay. So if you're within epsilon 1 of the input value G of X, H epsilon 1 guarantees that F is within epsilon of its value. That's the continuity of F, but not at X, at G of X. Now what? Yeah, let's work on HG, exactly. It's going to be a choose. At what point? At X, with what epsilon? Epsilon 1, H epsilon 1. This is the positivity. So maybe I should, yeah, H, whatever. There's the positivity, so maybe I'll call this epsilon 1 pos, and then H epsilon 1, so that I have that separately. So this will be epsilon 1 pos. This says there exists a delta. So give me that delta, choose delta, the fact that it's positive, and then the hypothesis on it.
What is H epsilon 1?
What is a very good. Let's record what H epsilon 1 says.
For all like X or for all Y. If Y, distance between Y and G of X.
Yes. Yes.
And F of is less than epsilon.
Perfect. Which Y will we apply this to? Well, we'll come back to that. We'll come back to that if it's not obvious yet. What about H delta? What does H delta say? All Y. Yep. Well, now it's delta. Yep.
G of Y minus G of delta, or G of X is less than
We get the epsilon that we fed into the continuity of G is epsilon 1.
But in H epsilon 1, we're using like only epsilon.
In H epsilon 1, we're saying as long as Y is within epsilon 1 of G of X, F of Y will be within epsilon of F of G of X.
Okay, but then now epsilon 1 becomes our.
Exactly. Epsilon 1 becomes the epsilon and delta. So that's exactly the thing. In order to get, so the delta that we want is this delta. Okay. So use this delta together with its positivity. And so now, given that, intro Y and HY. So Y is within delta of X. Therefore, if I take H delta and I feed into it, have I lost you?
Well, you lost me at intro Y, HY.
Okay. Let's put this much into the computer and see what happens. And then I think you'll see what's going on. If these pictures aren't helpful for you. So give me the x. I'll separate these because at least in my mind, they're separate. Of course, you could do this in one line. Give me the epsilon and the h epsilon. So we want to know that there exists a delta so that, as long as y is within delta of x, f composed g of y is within epsilon of f composed g of x. And what we're going to do is feed that into hf. So choose epsilon 1, the fact that epsilon, let's call this epsilon 1 pos, and h epsilon, let me not use the fancy one so that I have one less button to fumble. Using hf applied at which point? G of x, and with what epsilon? Epsilon and the positivity of epsilon, which I called h epsilon. Okay, fine. So that one I called h epsilon. Okay, so far so good. So epsilon 1 says for any y, as long as y is within epsilon 1 of g of x, f of y will be within epsilon of f of g of x. So far so good. We took that epsilon 1 now from, so if, as long as g wiggles by no more than epsilon 1, f will wiggle by no more than epsilon. How do we guarantee that g wiggles by no more than epsilon 1? We take x within delta. Yeah, we take y within delta of x. That's what the second choose is doing. So choose delta, the fact that delta is positive. Come on. And the hypothesis on delta using, I'm missing the word using here, of course, using hg at x with what wiggle room in g? Epsilon 1. And why is it positive? Because we said it was. Okay, does that make sense? So that's delta 1 says for all y that are within delta of x, g will be within epsilon 1 of g of x. Okay, so that's the delta we want to use. We found our delta. So use that delta and use the fact that it's positive. Now give me, now our goal says, okay, so do we have a y within, once we've said what the delta is, then it's given any y within delta of x. So that's an intro y, hy, intro y, hy. And now we have to prove that f of g of y, so we're here, why does f of g of y differ from f of x by no more than epsilon? So let's not be fancy. Let's do a specialize. We could do this in one line at this point, but it's chaining a little too much. So what do I want to specialize to? And so now I have my y. I have a y here, and I know that y differs from x by at most delta. Therefore, yes? Exactly. I have my y, which is within delta of x. That means I can get g of x to be within epsilon 1 of g of y. So specialize, yeah, let's write this down here first. Specialize h delta, which takes a value of x, to y. Is y within delta of x? Yes, that's hy. That's going to make h delta say g of y minus g of x is less than epsilon 1. Let's not be slick. Again, we could have done this in one step. Specialize h delta y hy. Okay, so now we know that g of y minus g of x is less than epsilon 1. So we've gotten ourselves to a position where we're within epsilon 1 of g. Now what? Beautiful. Beautiful. Here, the point that we'll take near g of x is g of y. G of y is the point that we'll take near g of x. So even though h epsilon 1 says for any point, if you're within epsilon 1 of g of x, what point do we want to put in? G of y. Okay, so that's exactly right. So I'll just write it here. Specialize h epsilon 1 to not y, but g of y. with what, where's the proof that g of y is within epsilon 1 of g of x? H delta. Okay. So specialize H epsilon 1 to the point g of y at what, and what's the proof that g of y minus g of x is less than epsilon 1? That's H delta. And that is exactly what we want. I think apply will do it, or do we have to do a change? Apply will do it. Cool? Okay, so some things are easy. Hopefully that was easy. We didn't have to do all that much. And now hopefully the next thing we have to do is also easy. It's also not so hard. Okay, so we've seen that composition of continuous functions preserves continuity. Composition of continuous functions preserves continuity. Let's see about convergence. We know it's not true for general convergence, but let's see about uniform convergence. All right. So our new definition is uniform convergence. A sequence of functions. What's a sequence of functions? It's a map from the naturals to functions. That's our little f, which is why I like to use capital F for the limit. So little f is f sub n is a function, and big F is a function. It says for all epsilon, there exists an n, so that once you're past that n, for all x, regardless of where you are, fn of x minus fx is less than epsilon. Okay? And then we want to show that the function capital F is continuous. So theorem, this theorem has a name, I'm sure. Continuous of uniformly convergent. So continuous of uniformly convergent. Okay? If f, which is a sequence of functions, converges uniformly to capital F, so that hypothesis is called HFF. So that hypothesis was called HFF. And what? Exactly. And for all n, Fn, when I stick in an n in here, I get a function from R to R. Is continuous. That's called HF. HF is for all n, the function Fn is continuous everywhere. Let's not worry about continuity on subsets. Of course, this works on subsets. Then the conclusion, the goal, don't I say goal or whatever? Then let's just write in English. Capital F is continuous. All right, let's work on the proof. We already did the proof. We did the proof when it failed, but now it's not going to fail because the same n will work for every value of y. Right? So let's try to do it. So intro x. So now we want to prove continuity at x. So the thing that we want to prove is f of y minus f of x is less than epsilon. That's continuity, as long as x and y are close enough to each other. So intro x, intro epsilon, and h epsilon. And now what? We already did this.
This is the point where we have to find a delta.
Yes, exactly. What delta should we use? Brandon.
The uniform convergence.
Yes.
We specialize the epsilon.
Yes. Okay. Yes. Let's specialize the uniform convergence to epsilon. Okay. So specialize. I like that. But let's draw a picture of what's going on. The FNs are converging to capital F. And the Fn of y's are also converging to capital F of y, and at the same rate. We can take one capital N where both of these will be small enough. Okay, so that's what's going on. Let's specialize what was this called? The uniform convergence, H, F, capital F. So this says for all epsilon, there exists an N. So let's feed it epsilon. Let's feed it the positivity of that epsilon. And that'll give us a capital F. So actually, we don't want to specialize. We want to go straight to choose. Choose N HN using this. You want to see this as we go along? Will that help you? Intro X, intro epsilon H epsilon. Okay, and then choose N HN using HFF epsilon H epsilon. So now we have a capital N, so that for all n greater than capital N, and for all functions, for all values, for all inputs little x, Fn of x minus f of x will be less than epsilon. Now what do I want to do? Yeah, where am I supposed to get a delta?
Definition.
We use the definition of uniform. It's right here. It's for all epsilon, there exists an n. So that for all n past that point, and for all x. So we already used that uniformity right here. We stuck in the epsilon and the positivity of epsilon. That gives us an n. And so Hn now says, as long as little n is past capital N, once you take little n large enough, this is within whatever you want, and this is within whatever you want, just by taking little n large. So where's our little n? Where are we going to get a little n? Just use capital N. We don't need it. We don't need the fact that you can take it even larger. We can just use capital N. So let's specialize Hn to capital N. Okay. Let's get rid of the little n. Little n is just an aside. Specialize H capital N to capital N to little n equals capital N. And why is capital N greater than itself? By bound. Okay. Does that make sense? So here, specialize Hn to capital N and by bound. All right. For all x, regardless of whether we're here or here, we can get within anything of f. But remember our argument. What was our argument? In order to get this to be less than epsilon, we're going to make this distance less than epsilon over 3. We want this less than epsilon over 3. We want this distance less than epsilon over 3. And then we want this distance less than epsilon over 3. And this Fn is continuous. That's where we're going to get our delta. Okay, so actually we don't want to apply the uniformity to epsilon. We want to apply it to epsilon over 3. And then the positivity will be by bound. Does that make sense? So let's just make that little change. I think it's easier to make it in editor mode. So instead of epsilon, I'll put an epsilon over 3. And then H epsilon won't do, but bound will. Back to typewriter. Okay, does that make sense? So now it's very simple. So we know what our capital N is. We know which function we're going to use, Fn. So where do we get this? Where do we get delta? Joe. Exactly. From HF specialized to which value of little n? Capital N, that's the only natural number we have. You just look at the set of objects. We only have one natural number, so that's the only one we can use. Exactly. So we stick in, so let's start with HF. When we stick in, HF says for all n, Fn is continuous. So we're going to use capital N. The fact that it's continuous everywhere is nice, but we don't want it everywhere. We want it with specificity epsilon over 3. But which point on the real line do we want to apply this to? X. So we have to give it x first because it's continuous everywhere. So where do we care about its continuity? We care about it at x. With what specificity? epsilon over 3 and by bound. And what will this give us? What does this say? What is continuity? There exists a delta. So choose delta, delta positive, and H delta using this. Let's do it. Choose delta, delta is positive, and H delta using HF specialized to N. That says the nth function is continuous. It's continuous everywhere. Where do we care? We care about X. Fine, it's continuous at X. That means no matter what precision you give me, what precision do we want to give? Epsilon over 3. And why is that positive? By bound. Then there exists a delta so that for all y within delta of x, the f is bounded by epsilon over 3. Cool? Everybody see that? Okay, so what delta do we want to use? Use delta and it's positive, delta pos. Try to record both things simultaneously. Okay, so we've got delta and delta pos. Now intro y and hy. Intro y, hy. Just record that here. Okay. Y is big F less than that. We need the triangle inequality thing, right? So I'm just going to say have F1, which is that absolute value of Fx minus Fx is less than or equal to absolute value of Fy. Let's see, let's put it in a favorable way. Let's say Fn, little f, capital N, y minus capital F of y plus little f, capital N of x minus capital F of x plus little f, capital N of x, y minus little f, capital N of x. You buy that? You buy all three of those? And I'm just going to sorry this in the interest of our sanity. Fy minus Fx is less than or equal to. If you can get within, I'm just adding and subtracting the same thing, Fnx minus Fx and Fny minus Fnx. Yeah. Sorry, is not available in the game. Okay, everybody believes this trio? Joe.
At this point, does that?
I have, and I'm not going to show it to you now. I have the tactic that will do it. It's in a later version of MathLib, and when I update the version we have to the later version, it crashes the game. And so there are people who are helping me port the tactic. It exists. It exists, and very, very soon, I hope, I'll be able to say, okay, there's a tactic that just does it for you. But it's totally within the realm of what's already available to us.
You got still limited.
Big F's the limit of the function. Okay, so just trust me, bro, on this, and let's keep going. So y is this small. So let's have F2. Have F2. Y is the first thing small. Fn minus Fy is strictly less than epsilon over 3 by what? H delta specialized to y. Yeah, so apply H delta. H delta, I have to stick in a value of x1, which is y. Y is this within delta, that's hy. And then, oh no, H delta gets me from Fn to Fn. H delta gets me the bottom. This last guy is by H delta. What do we need? Hn. Hn is that we're converging vertically. Hn is these vertical drops. H delta is the horizontal one. So it's not H delta, it's Hn. Hn specialized just to y. All I have to do is give it a y. And that tells me Fny minus Fy is less than epsilon over 3. And it's the same n for all the y's because of uniformity. Okay, so that's F2. Have F3. Let's do the same thing, but at x. Fnx minus Fx is less than epsilon over 3 by apply. Same thing. Hn at x now. It's true for all x. We have to tell it what x to apply it to x. And have F4. F4 is that Fny minus Fnx is less than epsilon over 3. And that's by applying H delta. Now, H delta is going to need a y. That's y. And the fact that y is within epsilon of x, that's hy. That's the horizontal distance is at most epsilon over 3. And then linearith F1 through F4. We'll pick up the rest. Linearith F1 through F4. Try it. Okay, so F1 we already put in. F2, have F2 is Fny minus Fy is less than epsilon over 3 by apply Hn at y. I'm going to copy this. Beautiful. That bound is at most epsilon over 3. F3 is the same thing with x's. Beautiful. And F4 is that Fny minus Fnx is less than also epsilon over 3. And that is by apply H delta to y, and y is within epsilon of x, within delta of x. Now we have all of our inequalities. We have one vertical drop, and one horizontal drop, and each of them costs less than epsilon over 3. So the trio of them will get us epsilon. Linearith. Come on. F1, F2, F3, and F4. Yes, completed with a sorry. Okay. Uniform continuity, the uniform convergence, rather. Uniform convergence. I have such a hard time with words. You always, I hope, know what I mean when I write things down and not the words that come out of my mouth. There are two different concepts, and we're getting to the next concept, which is uniform continuity. We're not there yet. Right now, we're talking about uniform convergence, which is a sequence of functions converging to another function, not just point by point, but uniformly. There's one capital N that will work for all values of x in the domain. Good? Let's go. Completed with warnings. I don't care. We're going on to the next thing. Yes. Integration. It's time. We're here. Yeah. Quiz. What is a Riemann sum? I guess I should give you a quiz. Oh, good point. Thanks for reminding me. We might run anyway. It's Thanksgiving. You can have there's no quiz. What's a Riemann sum? What's an integral? Let me hide all of this. We're up to integration. I found, by the way, that if you Google professor lecture yells function or something, because you remember Simplicios goes, functions, we're up to functions, let's do it. So integration, we're up to integration, let's do it. What is the integral? Integral from a to b of f of x dx. Who remembers Calc 1? Other than Joe. All right, our Joe. Let's do it. You've got a function. All functions are the same. They all do this. We've got 2 points A and B. How do I find the integral?
It's the antiderivative f of b.
Ah, the fundamental theorem. Okay, no, I want the definition. Yes. The fundamental theorems, we're getting to that. But what's the definition? How do you actually, how do I figure out the area under this curve? It's a limit. It's a limit as, let's say, n goes to infinity of what? It's a sum. Yep. What are we going to do? Tell me geometrically. You chop this thing into little pieces. Okay. This is called the Riemann integral. even though this is what everybody was doing before Riemann, but Riemann was the one who took what Cauchy was doing and said, hey, we got to do integration right too. And so these are called Riemann sums. And so every one of these has a width. So let's say we're going to break this into n pieces. What's the width of each piece? B minus A over n. So I'll have a factor of B minus A over n up front because they all have the same width. And what's the height? Well, do you want to take the left or the right Riemann sums? No one cares, but there's a correct answer. I would have said left. My entire life, I would have said, you know, the right Riemann sum is the work of the devil. And we're going to take the right Riemann sum. And you'll see why. Because the indices work better. Instead of 0 to n minus 1, it lets you go from 1 to n. And everything, there's no subtraction in the naturals. It's just so painful. And if you slide the, yeah, so the devil is here. What's the height? It's the right Riemann sum. Okay, so this is the point that I want to take to approximate this this area. So this is f evaluated. So let's say we're going to sum as I. It's a range. So I goes from 0 to n minus 1. So this is I equals 0. I'm going to take A and I'm going to shift over by I multiples of B minus A over n. That's how much each multiple is. Except I said we were going to shift. We started 0, so we're going to take the right Riemann sums. Okay.
You're already starting at 0. Can we just like where is the indexing issue showing?
The indexing issue shows up in formulas like this. A sum as I goes from 0 to n minus 1 of I. Anybody know what this is? The sum of the first. Yes. The sum, the one that you're familiar with, I'll just write the words. 1 plus 2 plus n is what? N times n plus 1 over 2. Everybody knows this formula. Okay, so this is going to come out to n minus 1 times n over 2. And n minus 1 is awful to deal with in the naturals, in lean. Subtraction isn't right. The naturals don't do, you know, we let them do some kind of subtraction. It's the wrong thing. So just take the right, take the right Riemann sum, not the left one. Because the most convenient thing is to do sum, our summation always runs on range, and range is from 0 to n minus 1. Okay? So that's the integral. So we're going to define a bunch of things. So now I can show you what we're going to define. Can I slide this over? All right, so we're going to define, given a function, 2 points and a natural number, we define this thing. This thing is called the Riemann sum. Riemann sum. Okay, it's the width, b minus a over n, times the sum as I goes, ranges in the range. That should not be an in, that should be a in, whatever, in range n, f of a plus I plus 1 times b minus a over n. So this definitions don't need hypotheses. Just like division by 0 doesn't need a hypothesis. It's when you go to use it that we will absolutely need continuity, something like continuity, in fact, something stronger. What's the stronger thing that we'll need? Uniform continuity, okay? Okay, so this is a sequence. You give me a function and 2 points, I give you a sequence. It's a map from the naturals to the reals. We say has integral f from a to b, and the integral is equal to I. So the integral from a to b f dx is equal to I is called has integral f a b I. Okay, it's that the function, it's the sequence that maps n to the Riemann sum of f and b, f a b n, has a sequential limit, and that limit is the real number I. I is the integral. And one more definition, a function is integrable on an interval AB if there exists an I so that the sequence of Riemann sums converges to I. Okay, so that's has integral, and then integrable on is you give me the F, you give me the A and the B, is that there exists an I such that the integral from A to B F dx is equal to I. All right. Let's compute our first, maybe this is a quiz. I think this is a good quiz. Let's compute our first integral. It says 0 to 1, but it's actually nicer if you do it from A to B instead of 0 to 1. So you don't have to keep casting 0 into the reals. It knows that A and B are real numbers. So theorem, A and B are real numbers, and we have a hypothesis, HAB, that A and B, A is strictly less than B. And the theorem says integrable on, which means you have to figure out what the integral is. The function that sends x to x, this is called the identity function, from A to B. Do you guys remember what the integral is of x? Yeah, so we should do a little sketch off to the side that says integral from A to B of x dx is what? And then that's the first thing you want to use, presumably. And then the question is, why is it true? What are you figuring out geometrically, by the way? The area of it would be a triangle if we went from 0 to 1. We're going from A to B. Parallelogram. You're figuring out the area of a parallelogram with one base equal to A, another base equal to B, and the height equal to B minus A. If you remember what those come out to. Middle school. While you do that, I'm going to fix a couple of things. This is good. This is good. Where did I have a typo? Oh, here it is. Better. Yeah, that's better. What's the answer? Yeah, it's exactly a squared over 2 evaluated from A to B, also known as b squared over 2 minus a squared over 2, also known as height b minus a times the average of the bases, a plus b over 2. You know this formula for parallelograms? Okay, so you know what to use. So step 1 is going to be use b squared minus a squared over 2. Now comes a little bit of algebra. Maybe this is too much to give you on a quiz. Well, do you want more time? You want to keep working on this yourself? Or should we do it together? We're going to run out of time. Let's do it together. Let's do it together. You guys had a head start. Okay, so that's the, let me just stick it in. Use b squared minus a squared over 2. Okay, so now we want to know I want to know that this sequence converges to this. So what? Intro epsilon. Intro epsilon, H epsilon. Give me the epsilon. Okay, so intro epsilon, H epsilon. And now I want to know that the Riemann sum, so this is going to be a Riemann sum, 1 over n, not 1 over n, but b minus a over n, a sum as I goes from 0 to n minus 1 of the function, well, let me write the general formula first, a plus I plus 1, b minus a over n. That Riemann sum has to differ from b squared minus a squared over 2 by less than epsilon. This is what we want. Okay, and f of anything is itself. So I can just remove f here. All right. I'm going to add a to itself n times. So this part contributes, there's a constant b minus a over n out front, and then just n times a. That's a times. Okay. And then there's, if we look at, let me do this in another color. If I do this together with this stuff that gets added on, that's plus, I have a b minus a squared over n squared times a sum as I goes from 0 to n minus 1 of I plus 1. So sum from 1 to n. Now, what is this sum? Yeah, n times n minus n times n plus 1 over 2. That's the beauty of this method. You see that?
Oh, you're doing plus one inside.
Exactly. Exactly. Because it's the plus 1. And so that's why we were taking the right Riemann sums instead of the left Riemann sums. So there's no subtraction here. No nonsense. Okay. Let me write this as actually n squared plus n. Okay, so let's just write everything. Let me go back to a normal color. So this whole thing is equal to absolute value. I have this part. I guess the n's on top and bottom can cancel. So I have a times b minus a plus, let me write this as b minus a quantity squared over 2. And then what's left over is an n squared plus n over n squared, which is a 1 plus 1 over n, if I'm not mistaken. That whole thing, we need to subtract off b squared minus a squared over 2. You agree with that? So that we should get from algebra. Exactly. The 1 over n is going to go to 0. How about if I take, so let's look at the rest of this stuff. What is this and this and this? So I have a times b minus a plus b minus a squared over 2 minus b squared minus a squared over 2. What must it be if there's any justice in this world? We subtracted that, it must be 0. Because this whole thing's supposed to go to 0. And the only term that's allowed to survive is this term. Because that's going to go to 0. And we have to make the whole thing less than epsilon by arch prop. By arch prop. What's that? Arch prop is yeah. If the right Riemann sum's the devil, arch prop is the angel in heaven that keeps the gift that keeps on giving. Exactly. So we're going to choose NHN using arch prop with what value of epsilon? So it's show something by bound. And what value of epsilon do I want? I want this whole thing less than epsilon.
You want 2 times epsilon over b.
Exactly. 2 epsilon over b minus a squared. And maybe bound will do it, maybe not. Everybody see that? Choose, come on, choose NHN using archprop. Show 0 is less than 2 times epsilon over b minus a quantity squared by, please bound? Yay, bound. Really bound? Yes, really bound. Okay, awesome. It knows that, it knows that A is strictly less than B, so at least they're not equal, which means okay, whatever, it did it. But don't look a gift horse in the mouth. Okay, so we have our capital N. That's the capital N we need to use. Use that capital N. Intro NHN. Once N is less than that, you do some arithmetic. So what am I going to say? I'm just going to say that this whole thing is equal to or maybe rewrite, show that this whole thing is equal to b minus a squared over 2 times n by, sorry. I know sorry is not available, but trust me, this whole thing, I mean, don't trust me. Do the algebra, but the algebra has, if we got this right, the algebra has to come out. I mean, let's do the algebra. Let's do the algebra. There's a b squared over 2. There's no b squareds here. There's a minus b squared over 2. That's got. What are the a squareds? I have a minus a squared. I have a plus a squared over 2, and I have a plus a squared over 2. The a squareds are gone. Let's do the AB term, the cross term. I have a plus AB. I have a minus, what? A minus AB and no AB here. So that's the algebra. We've done the algebra. Okay. So between ring and field simp and all that nonsense, we get down to here. And then, and then we're done. Oh, sorry. That's not right. This isn't actually true, as stated. That's not with a capital N. That's with a little n. That's with a little n. And because little n is bigger than capital N, and this is bigger than that, sorry. Okay, you see the point? So this whole thing, really, this should be with a little n. So once, intro, I'll just write intro NHN, and then rewrite show the goal is actually equal to, what did we say here? This thing, b minus a squared over 2 little n. And then need to show the new goal is b minus a squared over 2n is less than epsilon. But we know that n is at least capital N, and that 1 over 2 times epsilon divided by b minus a squared is less than capital N, which is less than little n, less than or equal to little n, which implies this. All right, you did your first integral. Guys, we're doing calculus.